so let's build this program. Basically just we moved the data allocation directives here as set of examples, and then we also have a couple of instructions. So essentially what we do is that we populate or load register EX with address of this 16-bit value in memory, and then we move EAX into variable right here, into the variable in memory. So we store this offset in this variable. Okay, so that's just an example of a couple of move instructions and a few allocation directives. And let's build this. Okay, and so the location of my program is right here. Okay, so this is the path to my program that was already built. And now one way to observe the binary codes of our program is to start debugging session and look at the disassembly view. And the second way is to actually use the utility to be able to dump the content of this program by using essentially reverse engineer our executable image. So my image is here, and in order to be able to use this utility, you need something that's called developer command prompt for Visual Studio 2019, or whatever the version of your Visual Studio is, right? So in order to use this utility dump bin, you have to start this Visual Studio developer command prompt. So normally I access it, it's part of the Visual Studio set of programs installed, but I typically type developer in the search box here, and you see that it shows me this. Okay, so so this is the command window here, and if I try to dump bin as an example, you see that this program is here. So let's try this sample, and the idea is to say dump bin disasm, which means disassembler, right? So we actually let's just finish this. So I'm just copying this, copy, and then paste it right here, dump bin disasm, and use the path to our program. Copy, and right here just right click and paste. So we can resize it by using Control and scroll the mouse. You can resize the font. And so our command once again is dump bin switch disasm, and then the path to the program that we're trying to disassemble. Okay, so this is a debug build, so it just dumps this crazy set of debug image information that's stored in this program. So basically debug build populates the program with a ton of different instrumentation, and let's see. So but at the top of our, so this is it prints to us that this is dump of file, and this is executable image file. It understands, and it's mostly populated with int3, which is like interrupt instruction that stops the debugging of the program, but it knows where the main begins, so the startup code jumps to main, and of course this is where the main is, so we have something very similar to what's being printed right here. So the actual image depends on the type of the assembler and the linker that you're using, but nevertheless we can recognize these commands that we have in our code. So I'll just try to put this side by side like this. So these are the two commands in main procedure that we have. And notice that as we discussed, we're trying to load the address of word 2, which is this, into the register. And so it just happens to be that the address of word 2 in my build ends up being hexadecimal 404002. And of course, what this results in that the result of this offset adjusted by the linker becomes an immediate value directly inside the instruction format, right? So this becomes an immediate value which follows the actual instruction opcode right here. So, but observe that this value that the disassembler shows pretty well, right, is stored in reverse order inside the command. So instead of saying 40 40 or rather 00 then 40 then 40 and then 02, it's backwards. It's 02 and then the rest of it. So this type of storage, okay, so this type of storage where the lowest byte appears to be in the lower memory address, because every subsequent byte is in the next memory location, and the next memory location, and the next memory location. This type of storage is called Little Endian. Okay, so that the value, when it's stored in memory, multi-byte integer value stored in memory, appears to be showing up backwards. Likewise, when we just used direct memory address of variable 8, which is a double word, which is an integer or it can accept memory addresses, its value is 00404008 hexadecimal. And again, it's stored backwards. So basically the way it's stored is this way, right? From right to left, you see that the highest byte is stored in the highest memory location, and the lowest byte is stored in the lowest memory location, because this instruction move, this is the compiled version of it, is stored at this address, and the dump bin shows us what the disassembled version or the actual opcodes look like. And that's the idea of byte ordering, and there are two versions of byte ordering. Basically, I think that we have a slide that shows a comparison right here. So for instance, word is 16-bit value, double word here is a 32-bit value, and this is another example. We're using on x86 platform, right, on Intel platform x86. What we're using is that we're using Little Endian byte ordering in a random access memory, and so that's how the values are stored. And if you think about it, what happens is that we have these 4 bytes, for example, that are needed to store an integer in memory, and we have a register where, for instance, like in our instruction right here, where this value originates. So one way to wire this memory, right, so this is our RAM, random access memory, okay, and this is our CPU register, right, so this is one of the registers like EAX right here. So one way to wire it is to store the lowest byte of the value of this integer value in the lower memory address. So if this is the lower memory address and this is the higher memory address, it's possible to wire it like this. Okay, like this. And this is an example of the Little Endian storage. Now, another type of storage would be that once again we have these bytes in memory. So we're storing a value like this in this memory. So we need 4 bytes to store this double word, 32-bit size, and this is our register. But this time, the way we wire our computer is that the lower byte, right? The lower byte we can attach to the highest byte, and like this, and like this, and like this. And the highest byte will be stored in the lowest byte of memory, because say this is the lower address and this is the higher address. So this type of architecture is called Big Endian. Okay, so when the low goes into the high, okay, and when the high register byte goes into the low. So this has nothing to do with the internal structure of the processor. Internal structure of the processor is just like we're using numbers, since we started talking about signed and unsigned numbers and 2's complement encoding, and the lower bit like bit 0 and the highest bit like bit 31 and all of this. Okay, so this is all happening inside the CPU. It's all the same, but the way the CPU may be wired into the actual RAM, there could be these 2 possible combinations, and the result becomes visible, right, when we disassemble the program like this, or when we load this program and start the debugging session. We observe that the actual integer values that we're using are stored backwards, and it's just basically byte by byte. So right here, the lowest byte once again is stored in the, right here, the lowest byte is stored in a lower memory location, and the highest byte is stored in a higher memory location. So this is Little Endian architecture, and it's supported on Intel. Most of your ARM devices that you use, like mobile devices, your cell phones and tablets, are using a RISC architecture. So they either are configurable to use Little or Big Endian, but most of the time Big Endian architecture is used in those devices. Big Endian is also very important for transmission of binary values over the internet. So in networking, Big Endian is a standard encoding of multi-byte quantities in memory. So for us, this becomes important when we're doing debugging of the program like this. We have to recognize values in memory and recognize that their storage, in our case on x86, is in this Little Endian format where the numbers will appear backwards. So this number 5, 6, 7, 8, 9A and so forth will appear backwards in memory. And we can also verify it by stepping into our program. So I just built this program and stepped into it. Okay, and if I show what is the address of variable 4, so this is my console window, I will clear it, and I type $, which is address of var4, okay, which is very similar to what we have in our handout, this value right here and right here, right? So it shows me that this value is stored in this memory. I'll just use this hexadecimal address, go to debug Windows memory, open the memory window, and type this address that I found in the immediate window here into the address bar, hit enter, and there you can see that my value, the number that we initialize variable 4 with this hexadecimal pattern, BC is the lowest byte, right, because it's on the right hand side, and it's stored right here, okay, in the lower memory address. And then comes 9A, and it appears to be in the next byte. So right, so this is the way it's all stored, like we try to draw in our demonstration, like this. Okay, so 5, 6 happens to be in the highest memory because it's the highest byte of this value. So once again, example of Little Endian, right? And if it was a Big Endian architecture instead of x86, 5, 6, 7, 8, 9, A, B, C would be stored exactly in that order in this memory, but we have it backwards. And so this is the difference between the Big and Little Endian architecture type of storage.